Mathematical modeling for optimize the supplier-driven demand. The predictive artificial intelligence models are implemented in the General Algebraic Modeling System, GAMS, and use IBM C-Plex as the optimization solver. Planning that drives demand? Demand controlled by the buyer, who decides the demand that must be followed by the seller. The buyer defines the market. Or demand that drives planning? Demand controlled by the seller, who decides the optimal demand to satisfy and how to do it. The buyer adapts to the market. From the point of view of organizational management, it can be said that the demand model and the production and sales model are the hypothalamus of the organization. How these two models are handled is the cornerstone of successful planning. A very good demand forecast, followed by regular production planning, or a regular demand forecast followed by very good production planning, will put the organization at risk. The modeling effort must be done in both directions. Buyer-managed demand modeling. Demand driven by the market. The term demand-driven was invented in 2002 at PeopleSoft. It was and is still defined as sensing changing customer demand, then adapting planning and production, while pulling from suppliers, all in real time. Under this approach, the organization's demand planning is done by the market, which determines what the organization should produce. The greatest effort is made in the demand forecasting model. Here's what traditional modeling might look like, from the integration of the two models. For all products, at all points of sale, for each of the periods of the planning horizon, the following process is carried out. The DEM model is used to estimate the parameters of demand models, with the parameters estimated for the probabilistic process average. Demand projections are made, and after a review of the projections, the pertinent adjustments are made, and the planning of the demand to be met is formalized. The next step is to use demand projections to determine the inventory policies, to be followed over the planning horizon. The final step is to run the SANDOP model, taking as input, demand projection, and inventory policies. The result of the SANDOP model will be the plan of the goals, production and distribution, to be achieved during the planning horizon. This process, despite being carried out with advanced mathematical models, may have many coordination problems. Some of them may be: since demand planning was done without considering all the constraints that need to be met in production, it may not be possible to meet it. Because demand planning was done without considering the economics of costs and benefits, it is possible to produce products that are undesirable, often because they force production to meet recklessly made commitments. Minimum inventories are planned for all products, even those that cannot be sold or produced, which can lead to further stress on the production system, and inventories may not have considered storage capacity management, leading to infeasibility in inventory policies. The above are some of the problems of coordinated planning, which can be solved with integrated planning. Demand driven by the seller, or driving demand. The term is used by HI to name its approach to integrated supply and demand chain planning. It can be defined as demand controlled by the seller, or by the producer, who decides from the potential demand which one should be attended, and how it should be met. Under this approach, the organization's demand planning is carried out by the organization, deciding what to offer to the market, taking its potential demand as a reference, but deciding autonomously and optimally what demand it wants to meet. The modern approach is to integrate the three models into one, so that planning is done holistically, and not segmented into three separate silos, which do not see what is happening next to them. The process to follow is: the SANDOP model is modified as follows. The algebraic equations of demand models, not projections, are the representation of demand. This is equivalent to taking the demand model to the SANDOP. In this way, the integrated model will be able to make demand projections internally. Demand equations are expected to include the elasticities of firm-controlled factors, so that the model decides the optimal value for these factors. The inventory model is integrated into the SANDOP model. With these changes, the SAND-OP model will produce, as part of the optimization process. The optimal demand projection, defined as the projection that is feasible to fulfill, and that produces the greatest economic benefits to the company, and optimal inventory policies, respecting storage capacities, and establishing policies only for those products that are part of the optimal demand projection. The fundamental result of the SAND-OP model will be the same as in the traditional method. The plan of the goals, production and distribution, to be achieved during the planning horizon. But it will be a realistic, feasible, and economically optimal plan. Demand forecasting with artificial intelligence. Forecasting aggregate demand in a sector, area, manufacturer, category, and/or channel, or combinations of the above, has two alternatives. Bottom up. The projection of aggregate demand is made at the lowest level of the grouping, at the level of the atom, which implies having the capacity, data and computing power, to estimate a statistical model for each demand series, product, point of sale, POS. Atoms relate to SKUs at a point of sale for a day. Top down. The projection is made at the level of aggregate demand, and then it is disaggregated at the level of atoms, for which it is required to have disaggregation rules, which are generally not self-evident, and therefore they are rules of thumb. If possible, High prefers the bottom-up method. From the point of view of the volatility of the data series, and therefore of the projections, volatility is expected to decrease at the aggregate level. However, the above is true if the demand correlation in atoms tend to have neutral or negative correlations. If the correlation is positive, the volatility of aggregate demand will be higher. The first step in structuring a demand model is to select the type of statistical model to use. The first models available were self-explanatory models based on time series of the Box and Jenkins type. The current models are exogenous models combined with self-explanatory models, based on the theories of Box and Jenkins, complemented by Garch models, and including exogenous variables. The generalized autoregressive conditional heteroscedasticity, Garch, model, is a statistical technique used to analyze time series data, if the variance of the error term, or the difference between the actual and predicted values, is serial autocorrelated. The demand for products, and/or services, is the result of the integrated impact of multiple factors. These can be grouped into economikos, prices, product and point of sale attributes, competitor activities, advertising, and seasonality of multiple kinds. This implies that a demand model that only considers consumption time series, and possibly sales prices, leaves out important effects that affect demand. For this reason, models based on simple time series, such as Box and Jenkins, need to be expanded to consider all the effects. The two main results of the DEM model are characterization of the competition, and characterization of the client. This is summarized in algebraic equations, which characterize the mean and the variance of the demand process, so that the characterization is probabilistic. To estimate all the impacts, more specifically the elasticities of demand with respect to the factors, it is necessary to add databases from different sources to the company's databases, depending on the type of market. As an example, the image presents information from the following types of databases: historical sales information, hydroclimatic databases, socio-demographic information, Nielsen, syndicated database, history of promotions, own and competitors, and seasonal events. Effects included. The model must allow the inclusion of different types of elements, to represent processes of demand for goods and/or services with very different behaviors. In DEM, the generic equation to explain the average demand is made up of the following additive components: elasticity of demand versus price, cannibalization, pantry loading, lost sales, time trend, periodic seasonalities, seasonalities of events or business initiatives, effects of global exogenous variables, effects of regional exogenous variables, autoregressive effects. moving average effects, product attribute effects, POS attribute effects, and zone attribute effects. With proper modeling, it is possible to decompose demand as the sum of the impact of the different factors. This applies to every product, every point of sale, and every period. For example, the demand may be broken down into base demand, competitor pricing and promotions policies, product features, seasonality, and company marketing policies. The elasticities of factors, which are under the control of the company, are essential to optimize the marketing mix and market share, and others marketing and sales decisions of the company. This implies that the process of sampling events, and in general the collection of information, must consider the activities that are planned to be carried out in the future. Therefore, the demand model aims to answer the main questions about market behavior. HiDem provides quantitative answers to questions such as: what is the immediate effect of marketing mix decisions, e.g., 2-for-1 promotions, space events, advertising investment, etc.? What is the impact of periodic events on demand, e.g., end of month, fortnight, Easter, day of the week, etc.? What is the impact of promotions in later periods? What is the effect of product features, e.g., colors, textures, etc.? What is the effect of point of sale features, e.g., size of the premises, floor, etc.? What is the natural level of growth in demand, without considering seasonality or marketing events? What is the impact of exogenous variables, such as climate, national GDP, or regional GDP, or population? What is the demand price elasticity of each reference? And does this elasticity behave seasonally? It is a question of individualizing demand in all its components. It corresponds to a proactive position of the seller in which, based on artificial intelligence models, the seller tries to influence buyers to make their purchases in response to the seller's actions. Some examples: targeted offers at the time of accessing a website, selection of the days on which the beer festivals will be held, determination of campaigns in the advertising media, choice of marketing campaigns according to the points of sale, and definition of prices according to the points of sale, the times of the day, and/or the events that occur, among many. The flow of the analytical process is data cleansing, prediction model, forecasting, selection of control variables, and optimization model. Control variables are decisions that have been defined, in the past, by the salesperson. For decision makers, a demand model with only uncontrolled variables is only informative, as the seller will not be able to manage the demand. An example of an uncontrolled variable, weather, and a controlled variable, promotions. In a traditional approach, the control variables are defined by the decision makers, based on their mental model, and therefore, directly or indirectly, are input data to the optimization model. In a traditional approach, the control variables are defined by the decision makers, based on their mental model, and therefore, directly or indirectly, are input data to the optimization model. Planning that drives demand, integrated modeling. Below is an example of synchronizing models to plan for access to new markets. The process begins with a demand model, capable of decomposing demand into multiple effects. In the case of new markets, there is no adequate information in the seller's databases. An alternative is to use a syndicated database to provide the information. For demand forecasting, the simplest and riskiest position is to assume that the environment scenario will be equal to the average values of demand, generated from the average values of the parameters, and the exogenous variables of the statistical models. This involves the input of a deterministic optimization model. A better optimization model consists of generating multiple scenarios of the environment, using a Monte Carlo simulation to generate synthetic scenarios, which will be processed by a stochastic optimization model, which takes the random scenarios as input. A better optimization model consists of generating multiple scenarios of the environment, using a Monte Carlo simulation to generate synthetic scenarios, which will be processed by a stochastic optimization model, which takes the random scenarios as input. If modeled in such a way that the optimization model determines the control variables, the input demand to that model will be reduced to the basic demand. In short, there are two steps to demand forecasting, the natural one, and the company-controlled one. In planning for access to new markets, the second big step will be to use a model to characterize the behavior of market share, and from there create a profile of the type of competitor that would be the seller in a new market, or the profile in a market in which it is already participating. A traditional model involves using the forecasting models in the first stage, generating standard projections, and these projections are used as input for an optimization model. Considered as a process, market share determination is the result of three stages: demand study, optimizing the marketing mix, and market share projection through an optimization model. The third step will be to use a production model to determine how the current supply chain, or an extended chain, would work, taking into account the new market. In this way, the three models together will support the decisions. Ideally, you want to combine the decision steps into a single model for maximum expected returns. The power of today's computers makes it possible to integrate mathematical models of all functions as an integrated problem of the entire organization, which should not be faced in isolation. To do this, it can be visualized that the result of predictive models are algebraic equations, which are usually converted into input tables to optimization models. The integration of the models can be carried out by including the algebraic equations of the predictive analytics models in the optimization model, in such a way that a single predictive prescriptive model is available. This implies that controlled demand scenarios are not exogenous but are generated by the model from the activation of the control variables. Although this model requires more computing power, in return it produces better solutions. In economic terms, this is a higher profitability. Following the methodological principles of artificial hypothalamus, a network of demand models can be built, which can operate autonomously, and in a distributed way, according to the administrative functions they support. This is a new way of looking at the same problem, but modernized to take advantage of Industry 4.0 technologies. Artificial brains, and more specifically the artificial hypothalamus, make it possible to integrate all models, in the same way that the human brain simultaneously faces all problems to ensure its existence and well-being. Planning that drives demand, integrated modeling. The production and sales model are the hypothalamus of the organization, the cornerstone of successful planning. The modeling effort must be done in both directions. The two models can be developed individually and then joined together, that is a unique property of OpTex. One aspect that should not be forgotten, due to its importance, is the organization and processing of the database, which includes several steps, almost all of them aided by artificial intelligence tools. In scientific marketing, there are many decisions that are based on optimization models. In the tactical planning stand out market share optimization, marketing mix optimization, and inventory policies. In operational decisions they stand out revenue management or optimal pricing, optimization of customer management, optimization of the sales pipeline, and marketing optimization campaigns. These models can have a version of tactical planning, which sets operational goals. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world."